Hi everyone. Hello everybody. Welcome to the last seminar of the semester. Today we are very pleased to have Dr. Dom Liu from the Department of Mechanical Engineering as our department speaker. Dr. Liu is a professor and the graduate and the director of graduate studies in the Mechanical Engineering department here. He has received his bachelor and his master's degree in mechanical engineering from the thermal engineering from the Single University, and he obtained his PhD, awarded his PhD in mechanical engineering from Purdue University. After which he joined University of Houston and has been there since as assistant and then full professor now. He is also the associate editor of the Journal of the American Society of Mechanical Engineers, Journal of Thermal Science and Engineering Applications, and has served as the chair of the ASME, that's American Society of Mechanical Engineers, Committee on Nanoscale Thermal Transport Processes. He has a wide range of research interests, including micro and nanofluidics, study of phase change, heat transfer, boiling, and two-phase flow, and as well as light matter interactions. So very, very excited to have you here today. We look forward to hearing your talk. I appreciate that. Okay. The stage is yours.
Yeah. Okay. Right. Good afternoon, everybody. I'm very pleased to be here. I guess when you first came in, look at the title. What's going on? Right? So I know you guys are civil engineers. Why you have someone talk about nuclear boiling heat transfer intensive? So I know everybody is busy and probably stressed because it's a final year. Right? So I try to pick something that's interesting and that's not so technically involved, basically to give you guys some amusement, to have enough energy to deal with your final year. Okay, right. So I'm from mechanical engineering, and my research covers phase change heat transfer. So here I want to tell you about something we did in the past few years. Okay. Right. So, okay, it happened. Okay, right. So this is outline of my today's talk. I will first tell you about the background, what is the problem we are trying to solve, and specifically I want to spend a few time or more than a few minutes on how we come up with the solution that I will talk about. Then I will tell you, how we perform the experiments and how the experimental result looks like. If we have time, I want to tell you a little bit about the theoretical modeling we've been doing. Then I conclude with some remarks. Right. Okay. Yeah, boiling. So I guess everybody know more or less about boiling. So if you have ever brewed a cup of tea or coffee, this picture is not something. So boiling is a phase change process, during which the liquid phase will be converted into vapor if the liquid absorbs a sufficient amount of thermal energy. So it is represented by the formation of bubbles. Right? So that's what makes the study very interesting. So let me show you a video. So when I say boiling is interesting, you may not be convinced, but look at the high-speed video we took. This tells you exactly what happens when you have a bubble formation, bubble growth, and a bubble departure from a smooth surface. When I was a student, I can spend hours looking at videos like that. It's simply good. So that's why the study of boiling can be, technical, can also be, artistic. Okay. So now, well, why do we study this? Boiling is good. Specifically here, I talk about so-called nuclear boiling, or nuclear pool boiling. So this is when you have a pool of liquid which is at rest. So there's no flow in the liquid. So nuclear boiling occurs in such a scenario. So now, if you have ever taken undergrad heat transfer class, there are 3 modes of heat transfer. Right? So conduction, convection, radiation. Now phase change is a different type. And in fact, depending on the context, you can see nuclear boiling is one of the more efficient or maybe even better the heat transfer mode than the other heat transfer mode I mentioned. Right? So why? To give you a simple example here, let's look at water. Water has 2 very important properties. One is a specific latency. So it is 2,480 kilojoule per kilogram. So this means in order to boil 1 kilogram of water, it can absorb this amount of energy. Right? So 2,438 kilogram, a kilojoule. Now, if you keep water as a liquid, and only rely on the so-called specific heat to absorb energy, you see the CP is 4.2 kilojoule per kilogram per Kelvin. So that means if you have the same 1 kilogram of water, you need to, when you raise its temperature by 1 degree or 1 Kelvin, it can only absorb 4.2 kilojoule, right? So now you see there's a big difference if you use a so-called sensible heat versus the latent heat, right? So obviously you can see, well, from this calculation, you can see that, let's say we want to dissipate or absorb the same amount of heat. So with the same amount of liquid or water. So if you rely on the boiling process, this is the amount of energy you can dissipate. Now this is the amount of energy you can dissipate by using the specific sensible heat. Now you see from fundamental thermodynamics, we know phase change can occur at constant pressure and constant temperature. Meaning at 1 atmospheric pressure, the boiling point will be 100 degrees for water. So at maintaining that temperature, you can dissipate this amount of energy. Now, if you want to do the same, the water temperature rise must be as large as 600 degrees in order to do the same, right? So from this, you can tell nuclear boiling is appealing, especially because it is capable of transfer enormous amount of thermal energy with a very small driving temperature difference. So ideally there's no temperature rise at all. So if you maintain the process to be at 100 Celsius at 1 atmospheric pressure, you can transfer a lot of energy. So that is why it has been heavily used in industry, right? So you see the first picture is actually the original design of Watt's steam engine. So that basically powered the modern civilization. Then people we are still using boiling in the nuclear power plant, right? So move on to a newer technology. This is desalination for seawater. We rely on boiling process to convert the salty seawater into clean water. Now, if you go to a data center nowadays, you can see people are using so-called immersion cooling to make sure the servers are operating at the below a certain temperature limit. Okay, so these are the application background of boiling. Now, ideally speaking, what kind of boiling performance do we have? We can see that from the so-called boiling curve. So basically, it is a graph constructed of using a wall heat flux. So this is watts per unit area as the vertical axis, and the wall superheat. You can also think of this as the temperature of the wall, right? So that is also the temperature of the device, which we use to transfer heat. Right? Okay. So now here is a curve. It basically says in order to dissipate a thermal amount of energy, or what is the price you need to pay, right? So in order to dissipate this amount of heat, this will be the surface temperature you have to afford, right? So obviously, the ideal case will be once boiling occurs, we want to, basically pay nothing, right? So once boiling occurs, right, we want the wall temperature to maintain at a constant value. Now, even when you further increase the heat flux, so the wall temperature doesn't increase. So basically, as far as there's water, the temperature always maintains. Let's see at 100 Celsius at 1 atmospheric pressure. Right? Okay, so this is the ideal case. So from performance point of view, you can see if this for this ideal scenario, the nuclear boiling, right, so can occur at a very low water temperature. Right? So this curve represents the liquid water. Right? So in order to gradually increase the heat flux, the wall temperature must increase. Right? But not for customer electronics. The temperature of the chip cannot exceed 85 Celsius. So going beyond that temperature will cause damage to your device, for example, your cell phone. Okay. Now, the second, we want the boiling curve to be vertical. Right? So basically, that means even though you are dissipating more heat, you no longer pay any further price. Right? So the wall temperature maintains a constant value, and also there's no limit. So you can go, to whatever, however high it can be. Right? So this is the ideal case, but in reality, it's never ideal. Right? So the actual boiling curve of boiling is something like this. So when at a low heat flux, the fluid remains as a liquid phase. Now, when the heat flux reaches a certain value, you start to see the first formation of bubbles. So that is also called OMB, onset of nuclear boiling. Right? So that keep on increasing the heat flux will cause the operation point to move on along this curve. So it's not vertical. So here you see the first formation of bubble. So the further increasing heat flux cause more and more bubbles to form at the surface of the device. Now it has an upper limit. So here we call this heat flux the critical heat flux. So this is where basically the entire surface is packed with bubble, right? So further increase the heat flux means more vapor will be generated. So you can imagine those bubbles will start to interact with each other. So they will agglomerate, form bigger bubbles. Now, once you exceed the critical heat flux, so something very bad will happen. So let me show you the video. So at that point, the entire surface will be covered basically by a layer of continuous vapor film, right? So you no longer have discrete bubbles. So this surface is under constant cover of vapor, right? We know vapor has very low thermal conductivity. Right? So basically, you are insulating the heating surface from the cooling liquid. Right? So the result is the temperature of your solid surface will increase dramatically. Right? So to some extreme case, you see this is a wire being heated, by Joule heating, and when it reaches the critical heat flux, further increasing the heat input will cause the transition from the so-called nuclear boiling to fume boiling. Right? So then you see actually the wire is burned out. So this is a very catastrophic effect. Right? So overall, the limits for nuclear boiling can be summarized as following. Right? So one more thing I did not mention, that is, if you look at the slope of the boiling curve, so heat flux divided by the temperature difference, that will give you the so-called boiling heat transfer coefficient. So that measures the effect of boiling heat transfer. Right? So because this boiling curve is no longer vertical, so the boiling heat transfer coefficient is not as good as we want. So it's the low value can be improved. Second, because of the existence of a critical heat flux, so there's an upper limit. So even compared with the theoretical limit, we can only get about 10%. With the condition we can afford in the laboratory, and the simulation or calculations reveal that if you can somehow increase the critical heat flux CHF by 30% alone, we can increase the power density of a pressurized water reactor by 20%. For the electricity generation in US, 17% comes from nuclear. Right? So if you see if we can improve CHF, how much more energy we can generate. We can improve the energy security of the country. So that's an important problem we want to deal with. Right? Okay, so next. So to enhance boiling, there are many different things you can do. Now, for our research, we picked on the surface wettability because it is an important factor that plays in almost all aspects of boiling. So including onset of nuclear boiling. So this is the start of boiling. Then the nuclear boiling heat transfer. This is during the midpoint or the mid process of boiling, and then also affects the critical heat flux. So that is at the upper limit of boiling. Right? Now, what is surface wettability? So it is a measure of how well the liquid can wet the surface. It is usually represented by the so-called contact angle. So here I have a flat surface deposited by liquid droplet. So the contact angle is measured through the liquid side of the liquid vapor or liquid gas interface. Right? Now, the same picture can actually be found in a boiling system. So here I have a vapor bubble. So following the same definition, so this side is the liquid side, right? So the contact angle is measured like this. Right? Okay. So basically, when the contact angle is less than 90 degrees, we call the surface hydrophilic. So that means it can be wetted relatively easily by the liquid. Otherwise, we call the surface hydrophobic. So specifically, if you're interested in micro nanotechnology, if the contact angle becomes less than 5 to 10 degrees, you can call the surface to be super hydrophilic. Now, if the contact angle gets greater than 150 degrees, you call it a super hydrophobic. Okay. So now the question is, we have the choice of using either hydrophobic or hydrophilic surface to impact boiling, but which one is better or which one is good? You want the surface to be wetting or non-wetting? Right? You guys can think. And next, I give you, some of the results people found from the literature. Okay, so now let's start from onset of nuclear boiling. So for bubbles to form, there's an energy barrier that must be overcome for the nucleation process to take place. Now, this energy barrier can be calculated as this. Right? So here, the theta E is a contact angle, right? So remember, which represents the viability of the surface. Then here, this sigma is the interfacial tension. Re is basically the size of the so-called nucleation site, the size of nucleation site. Okay. So I can plot this S as a function of contact. You see, for very hydrophilic surface, the F factor is big, right? So as big as unity. Now, as far as the contact angle exceeds 150 degrees, so this F factor almost approaches 0. So that means you have a 0 energy barrier. Basically there's no energy barrier for the nucleation to occur. So that also means the nucleation process becomes spontaneous. So that's why when you read papers, there are a term called nanobubble formation, nanostructure surface at room temperature and room pressure condition, right? So there's no heating. Why do you have bubbles? So the reason is exactly like this, right? So there's no energy barrier. So the bubbles can form spontaneously, right? Okay, so from this point of view, you can see hydrophobic surface, because it has lower energy barrier for nucleation, so it is better to promote onset of nuclear boiling. So that is good. Now, we care very much about the nuclear boiling heat transfer, right? So that's what we rely on to harvest energy, to dissipate energy. So the high heat transfer coefficient, boiling heat transfer coefficient depends on many factors. For instance, the nucleation site density, bubble departure size radius, the contact line motion, et cetera, et cetera. So specifically, if you look at how many nucleation sites you could have per unit area, it is it can be described by this equation. So basically, you can see if the surface is hydrophobic, you have a obtuse contact angle, right? So this guy will become greater than unity, right? So that means super hydrophobic surface is favorable to have have a larger active nucleation site density. Now, the other parameter is the nucleation site. So that is per unit time and per unit volume, how many boiling nucleation events you could have. So obviously, the bigger this G factor is, the more bubbles you will likely to see. Right? So now, this equation is very complicated, but if you examine the impact of theta, contact angle, and F, that's the factor we see before, the conclusion is, hydrophobic surface is better. It will give you a higher nucleation rate. Now, the other factor is the so-called bubble departure. Right? So having more bubbles is not necessarily good, because once the bubbles are there, they will block the flat contact between the liquid and solid surface. Right? So you want the bubble to form easily and leave the surface as soon as possible. Right? So that's why the bubble departure comes into play. So there are two factors for bubble departure. One is the departure size. Right? Departure size is proportional to the contact angle. Right? So basically, on hydrophilic surface, you have small bubbles, and on hydrophobic surface, you have a big bubble. Now, the key factor is the departure frequency, because the product of the departure frequency and departure size is a constant. So that means bigger departure size will give you smaller departure frequency, vice versa. Right? So that means if you have a hydrophilic surface, you have a smaller d, but you would have a bigger h, f. Right? So the bubbles can form and can leave the surface more rapid. So that is good for boiling. Okay. Now, when it comes to critical heat flux, so hydrophilic surface will win out, because when the surface becomes hydrophilic, it will constrain the motion of the contact line at the surface, because the liquid likes to stay in place. Right? So that will confine the expansion of the footprint of the bubble, so that it's less likely for the bubbles to agglomerate and form a vapor film. Right? Okay. Yeah.
Can the surface also affect the nucleation site density? Here you're talking about the hydrophobic and hydrophilic contact angle. But what about the surface?
Yeah. Yes. The question is, the nucleation site density depends on if you have a perfectly smooth surface. So there's basically nowhere for the bubble to form. So if you have some little piece, so imperfection in the surface, that will also contribute to the well, that will give you more nuclear impact. Now, variability because the surface rock affect variability. So these two are intricately connected. So yeah, they will affect. Okay. So overall, we can examine the impact of surface variability, which actually plays a very intricate role in the nuclear boiling. Right? So from the onset of nuclear boiling point of view, well, let me go through all this. So there are three factors, like I said, the beginning of nuclear boiling, OMB, and the end of nuclear boiling, CIVE, and in the between, which concerns the performance. So you can see hydrophobicity helps OMB, and hydrophilicity helps to increase the CIVE. Now, the heat transfer in the middle is a more complex problem. So the contribution due to surface variability can be one way or the other. So at the end, we are left with a dilemma. So we know hydrophobicity promotes OMB, but on the other hand, hydrophilicity enhances CIVE. But a surface cannot be both hydrophobic and hydrophilic. And so you have some conflict of interest here, right? Okay. So well, some experimental results can further illustrate this. The blue dots here represent the data for a hydrophobic surface. Right? So this is a boiling curve. So heat flux versus wall superheat. You can see that OMB occurs very fast. Right? At wall superheat of about 4 degrees or 4 Kelvin, you have the commencement of boiling. And the CIVE is very low. So below, this is what 250 kilowatts per meter square. Now, if you switch to a hydrophilic surface, you see it takes a lot more wall superheat. Right? So superheat becomes like 15 Kelvin for boiling to initiate, but it has a much higher CIVE. Right? So it is as high as about 800 kilowatts per meter square. You see the big difference. So looking at this, it is very natural for you to ask the question, can we graft the performance of both surfaces, right? So at a low thermal load, at a low heat flux condition, we want to utilize the performance from hydrophobic surface, and at a high heat flux, we want to utilize the performance of the hydrophilic surface. Right? So can we do that? So in fact, well, you guys can think if that's doable or not, right? So in fact, people are doing that. So we can structure the surface either chemically or structurally to introduce, hydrophobic section and hydrophilic section. Right? Okay. So chemically, you can, for example, make the background hydrophobic or hydrophilic, and add, coat the small dots or small spots with hydrophobic material, right? So that the nucleation can occur on these hydrophobic islands. And the large hydrophilic background can ensure you have a good CIVE performance. Now, similarly, you can use a so-called hierarchical micro nanostructures. So here, you have a microscale structure and nanoscale structure. So the idea is that the microscale structure can serve as a nucleation sites, whereas the capillary wicking in the nanostructure can help to make the surface very wet, so that you can enhance CIVE. Right? So this is a very natural thought. Now, does the idea work? So actually, it works. So here, let me show you some examples. When you have a hydrophobic surface, right? So this is the performance curve. Now, when you have hydrophilic surface, this is a performance. Now, what if we have the hybrid surface? Right? So this curve, the red curve, represents the hybrid surface. So at a lower heat flux, you have performance very close to the hydrophobic surface. Whereas when you have very high heat flux, the performance is even better than the pure hydrophilic surface. Right? So it works, but there are some very important deficiencies, drawbacks. For instance, those are micro nano fabricated surfaces. The design, the fabrication, everything can be very complex and can be costly, right? So not cost effective. And also they are very difficult to optimize. So unless you have a very clear understanding of the boiling process, otherwise you don't know what parameter to optimize. Right? So there are so many parameters you can work with. And also the over time, the micro nanostructures will age, right? Falling, contaminations will easily damage the purpose of these structures. And more important, the boiling process is actually a dynamic process. So for example, today is fairly warm, but yesterday it was fairly cold. So thinking about this from a power plant point of view, so their thermal load will fluctuate. So that means the heat flux you need to deal with, maybe in the low range, maybe in the moderate range, may also be the high range, right? Now, once these structures are made, they either work better for the low heat flux scenario or for the high heat flux scenario. You cannot dynamically tune that. So the question we are trying to ask ourselves is, can we actively control the spatial temporally dynamic boiling process? Can you change the surface availability in the time domain rather than in the space domain? So that's the question we want to answer. So our solution is, well, yes, we can. We want to use a so-called electrowetting to dynamically tune the surface variability. So here, the idea is to apply an external electric field to change the surface variability. Okay. So, well, here I show you a device that will allow us to do this. So, for example, we have a silicon substrate, and the yellow bar represents the electrode. Then this light gray area material is dielectric material. So that is to ensure the liquid is not being directly connected to the metal electrode. Then on the top we have a layer of Teflon. So that is to make the surface hydrophobic before you apply the electric field, right? Okay, so how it works? Let me see. Here I have a droplet that is deposited onto this Teflon-coated electrowetting device. Okay, you see, before the application of the before we apply the electric field, right? So if you measure the contact angle, it is obviously I don't know, maybe 110 or 120. So because the surface is hydrophobic. Now, once you apply the field, you see the contact line moves out and the droplet relaxes. And if you now measure the contact angle, we reduce it to, I don't know, maybe 80, 85 degrees. So it crosses the boundary between a hydrophobic surface and a hydrophilic surface. Okay. So what is why does electrowetting occur? So there are different theories. One perspective is to see that because of the application of the electric field, the surface free energy will change. Right? So nature prefers a minimum energy state. So that's why when you apply the field, the droplet must spread out to cover the more energetic solid surface. Now, there's also a mechanic or mechanistic perspective. So that is, when you apply the field, there is a electrowetting force acting on the contact line, so which is the edge of the drop. So that forces the drop to spread out. So regardless, the overall effect of electrowetting can be described by this guy, Gabriel Liebman, back in 1875. The equation is also Young-Liebman equation. So by the way, Liebman won the Nobel Prize in 1920 something. Right? So for something related to photography, yeah, not for electrowetting. Okay, so the equation tells you that theta zero is a so-called inherent contact angle, right? So that is when you pick the liquid, when you pick the solid material, right? So that's a fixed contact angle. Now, in the second term, this V is applied electric potential, and this D is the thickness of the dielectric layer, and this sigma is interfacial tension. Right? So after you apply the field, the contact angle will change from theta E to theta A. We call this the apparent contact angle. So you can see the effect more clearly from this graph. So at 0 voltage, so 100, I don't know, 117 or something, well, roughly 110 is an inherent contact angle. But as you increase the voltage applied, the contact angle gradually reduces, but it cannot go all the way down to 0 because of the so-called contact angle saturation effect. So this is because when the contact angle spread to a certain extent, it becomes unstable because of, for example, the fringe effect. So the local electric field may become too large, so that the interface and the contact line become unstable, may break into small droplets. Right? So the electrowetting effect will disappear. Right? So yeah, anyway, so you can see we can indeed change the contact angle by tuning the applied voltage. Okay. So we did some numerical simulations and experimental investigation to show indeed we can observe the electrowetting. First, the DC field can be applied. So the left side, you see the experimental measurement, and the right side, the right side shows the numerical simulations we did, kind of, to see if we correctly capture the important physics. Now, another very interesting phenomenon is we can use AC field to generate and control electrowetting. So here you can keep the root mean square value of the voltage constant and vary the frequency. So let me show you two videos. This is at 32 volts, and the driving frequency is 28 hertz. Now, when you increase the frequency, the interfacial oscillation becomes very different. So if you keep on increasing the frequency, you could have more than P2 mode, P4 mode, and you can have P6, so on and so forth, many modes. Right? Yeah. So this means indeed we can change the contact angle by using DC or AC electrowetting effect. Now the problem is most of the results available in the literature have been obtained by playing with droplets. Right? But that's not the focus of our work. So it's the same liquid vapor interface, but we are concerned with bubbles, right? So the effect works for droplets, but it may not work for bubbles. So we did some study to see if it works. So luckily we found some paper. This is before we started the project. So a paper said, in fact, you can use the same electrowetting to reduce the contact angle associated with the bubble. So you can reduce the contact angle from 120 all the way down to 7. So it's not a lot, but it is significant, because that means even for a bubble, you can cross the hydrophobic to hydrophilic threshold. Right? Now, more interestingly, we found another paper which utilizes the AC electrowetting to modulate the droplet, the bubble. So you see the bubble motion is not clear, but the so-called streaming flow at specific driving frequency becomes very obvious. Right? So this is also important for boiling, because if you look at the boiling heat transfer mechanism, right? So the bubble, if the bubble can act as a pump, right? So here, it generates the flow around it. Right? So that means you can have better mixing between the hot fluid near the wall and the cold fluid in the far away. So that it will help to further increase the boiling heat transfer. Right? So with this, we decided indeed we can modulate or enhance boiling with with electrowetting. So here, even before we do the heat transfer study, we look at the AC effect on bubbles. Right? So those are bubbles, no longer dropping. Right? You see, as root mean square voltage of 53 volts at 10 hertz. This is what you see, for a bubble and room temperature. Because this frequency is very, very slow, as you can actually see in real time how the bubble responds to the electric. The contact line is moving. It's like the bubble is shaking. Now we increase the liquid temperature to 100 Celsius at room temp atmospheric pressure, because this is what we actually need for boiling application. Basically similar behavior. Now when you further increase the frequency to 100 hertz, you start to see the oscillation of the interface. Right? Now imagine there will be flow generated around the bubble, right? So that serve as some sort of agitation to the fluid. Right? So that is good for heat transfer. Right? Okay. So now we need to examine if indeed the idea works. So for that purpose, we constructed this experimental apparatus. So we have a boiling chamber made of aluminum. So inside the key part is the electrowetting piece. It is made of 3-inch silicon wafer. I will not go through all the details, but we use silicon itself as the electrode, because it's very conductive, right, to generate the electrowetting signal. And also at the backside, we deposit the chromium thin film heater, because boiling you need the power input, right? So that is coming from the heater. Now for the measurement, we have two circuits: one to control the signal for electrowetting, and the other one to power the heater. Now for measurement, we have a high-speed camera to monitor the bubble dynamic. Right? So we want to see how the bubble motion will be affected by electrowetting. And also we have a high-speed infrared camera. So, we are concerned with temperature. Right? So we want to dissipate, let's say, 500 watts. But how does the temperature change? So we do not want the temperature to be so high that the silicon wafer be damaged. So by the way, when we exceed the CIVE, we actually observe the cracking of the silicon wafer. It was a mess. Okay. All right. So these are the experimental methods. So okay. Then let me talk about some results. So at a low heat flux, you can compare the bubble dynamics for a bare surface with a surface modulated by electrowetting. Right? Well, these are real-time picture. This is a playback at a lower frame rate. But in general, you can see on the bare surface, the bubble will stay here for a very, very long time. And when it departs, it has a very big size. You can read the number is a real time. And so here you can compare the numbers. So with electrowetting, we can increase the departure frequency by probably tenfold, and also the departure size becomes much smaller than what happens on the bare surface. You can see over the same time frame, this bubble still stays, but you have multiple bubbles already formed, growed, and departed. Right? Now, in the so-called fully developed nuclear boiling scenario, so this is very close to the CIVE, right? So you see, well, look at the videos and images on the left column first. So here at this same heat flux, you see the surface is pretty much covered by a big bubble. Actually, underneath you have a dry layer. And if you monitor the temperature, you can verify. So the maximum reaches about 100, well, I don't know, 110. Now we also extract the heat flux from the image. So you can see the red part of the high flux region. Now the blue color region is a region where the heat flux is low. Therefore, there's not much heat transfer occur because that region is being covered by the dry vapor. Now with electrowetting, you see at the same condition, you no longer have a big bubble hovering over the surface. Instead, you start to see the reappearance of the individual bubble. So you can see, there's no more big hotspot. Instead, you have smaller, separate hotspot. Right? So that is good for heat transfer. Also, overall, the heat flux of the surface is enhanced. Okay. Now, what's more significant occurs at the critical heat flux. So now this time, the heat flux is increased to 82 kilowatts per meter square. So let's see what's going on. Right. So you see now very clearly the surface is covered by a liquid film. Right? Now the big hotspot has a highest temperature of about 155 Celsius. So at some point we will trigger the electrical signal. Right? Okay, now you see this time the film breaks down into individual bubbles, and that the big hotspot breaks down into very much smaller pieces, and the maximum temperature reduces from 155 to 114, 112. So let's see the pictures again.
I can say the simulation of infrared.
This is the infrared camera. Each pixel is about 25 megs. So the full frame is 550, 5.
Matrix is the sum minus 2 degrees.
Okay. The matrix effect is 1 for infrared to reach 0.5. So the spatial resolution is 25 per pixel. Okay, so if you look at this again, this is a film boiling. So the entire surface is covered by film. Maximum temperature very high. Then we the vapor film disappears. You see the individual bubbles. Okay. So to see the effect more clearly, let's move on to this slide. So this tells you the average temperature of the entire boiling surface as a function of time. So before the electrowetting effect kicks in, the average temperature is 135 degrees. Now after it reduces to 110 degrees. Now the amazing thing is how quickly this can happen. So basically, once you click the button, within a fraction of a second, so 0.74 seconds, you can change the temperature by so much. Right? So that illustrates how effective the electrowetting effect is in terms of enhancing boiling. Right? Okay, so now look at the entire boiling performance. So we can, from the boiling curve, without the electrowetting, this is the performance. Now this is what you have with the electrowetting. So you can see the electrowetting delays the occurrence of fuel boiling. It enhances CIVE, and overall it also increases the boiling heat transfer coefficient. So overall, the effect is very good. So now the next question we need to ask is why. Right? So we know it happens, but why it happens? So for nuclear boiling regime, we have some very more obvious answer, because there's a electrowetting force acting at the contact of the bubble, so the bubble dynamics will be affected. So that will help to change the departure dynamics, therefore enhancing transfer. Also, because of the oscillation of the bubble interface, there's enhanced metro convection that will also help to increase the heat transfer. Now, the other mechanism is that when the contact line moves, basically affects because there you still have the pure liquid, so it's a so-called the transient conduction process. So the electric actually will augment the quenching heat transfer. That again increase the heat transfer. Now, the bigger problem is how does electrowetting enhance a critical heat flux? Okay, so for that we develop a model. These two sets of images tell you in detail what happens with electrowetting when the heat flux reaches CIVE. So the first image are from the optical image. So you see clearly the disappearance of the vapor field and the reappearance of the vapor bubble. Now the second set of images tell you the temperature. So these are the observations. Now behind that, we need to understand what actually contributes to CIVE. So there are two. Well, I will go very quickly here. There are two sets of theories. The first set is the so-called far field perspective. So it attributes CIVE to what happens at some distance from the surface. So basically, when the bubble, when the vapor leaves the surface in the form of a vapor column, right? So if the heat flux is very high, so the generation of the vapor content becomes so violent that the interface of the vapor column becomes unstable. And so the hydrodynamic instability causes the vapor column to collapse, so that you end up with a big bubble, so-called the mushroom bubble, to hover over the surface. So that will block the colder liquid to retouch the surface. So this is the far field theory. There's also so-called near field theory. So that attributes CIVE to what happens near the surface. So for example, it acknowledges the formation of the giant mushroom bubble, right? But it says the bubbles are actually connected to a thin layer of liquid at the surface. So the bubble can grow because the thin liquid film continue to feed the vapor content to the bigger bubble. Right? So now the dry out or the CIVE occurs when this liquid film completely disappears. Right? So you have the two different type of perspectives. Now later, there's the one unified theory. So that connects the far field to the near field theory. So basically the idea is we look at the force balance on the bubble. So the forces include, of course, the hydrostatic force, the surface tension force at the contact. So that tends to hold the bubble in place, right? So prevent the bubble from expanding. And also there's so-called recoil force. So because the vapor, the liquid molecules will leave the liquid phase and be ejected into the vapor. So it's like when you shoot a bullet, and so you feel the recoil force. So this is exactly what happens. When the vapor molecules enter the bubble, it will push the liquid vapor interface backward, right? So when the recoil force overcomes the surface tension and the hydrostatic force, the footprint of the bubble will expand. So it has a higher chance to agglomerate with bubbles nearby. And so this is a fundamental reason for CIVE to occur. Right? Now, in this unified theory, it considers the bubble dimension, like the diameter and the height, to the hydrodynamic instability. But it attributes the expansion of the bubble to the contact angle. So that's far field, near field effects together. Okay. So now by using this theory as the framework, we were able to show that with the electric field, we can change or we can reduce the contact angle. Therefore, we enhance the near field effect. And also with electric field, we can reduce the wavelength of the hydrodynamic instability. Further, because of the electric field, we can generate an additional electric force on the entire surface of the bubble, so that that pushes the bubble inward, so that in a way counteracts the effect of the recoil force. Right. So with all this, we can improve the surface wetting, amplify the interfacial instability, and induce the interfacial stretching, and therefore lead to CHF enhancement. Right? So I will skip through the next 3 slides. So each one detailing the 3 impact I mentioned. Right? So this is the hydrodynamic instability. This one is the electric force. So at the end we compare the model prediction with the theory. We see very good agreement. So I mean our model does capture the important physics. Right? So to summarize what I said, we demonstrated that the nuclear bonding heat transfer can be enhanced by electrowetting, and we developed a mechanical model to understand the electrowetting induced CHF enhancement. Right? So this basically is all what I want to talk about. I need to acknowledge my collaborators, Dr. Ruchal and Dr. Jimmy Ball from WE on the 3rd floor. Right? And our students, well, we graduated 3 PhD students from this project, Dr. Sir, Dr. Lu, and Dr. Paskani, and the financial support from SF and the University of Houston. So if you are interested in more details, I have a few papers here, and then I want to take any questions you may have. Thank you. Yeah, you can ask anything. This is not a test, right? Also, the last seminar of the semester, you can ask whatever.
So the infrared camera is not only you can sense the temperature on the solid, and also sense temperatures in the liquids.
Yeah, but it will be less sensitive because we need to correct the certain.
Yeah.
But you for liquid,
Calculate first.
you need to, yeah, you know, you can. If I would try to try a lot of probably at one point we want to try, for example, manage jumping from we try to temperature all of the I know this is very far from where
So again, I work on thermoregulation using vascular systems. So when we want to measure the speed transfer coefficient, they always say it's very secret. So let's say if you take a sample, I know what is the flux I'm providing. I can infrared, I can find out the millisurface temperature. But there could be losses on the long run. Even if you put foam or whatever it is, there will be loss. What is the what is the most accurate way of measuring heat transfer coefficient for these kinds of systems?
So I would say, well, there are the problem of coming to different mechanisms to work. I would say a little bit of heat transfer can be needed, right? If you can make, so there comes the problem. So when you measure temperature, you do some probably the plus. So you may not get the place where you're in. Now, if you can use you can compare, you can keep up the temperature. Now, the problem is with the air. What do you mean to do?
So basically, just to give the dimensions, let's say you have 100 mm by 100 mm, the carbon fiber is plastic, and you have a thickness of 5 mm. And at the bottom, you have a heater, this is to heater. At the top, you have a product. In the Excel, you can get the temperature. So you can locally calculate probably the heat transfer coefficient, Q divided by delta T.
Yeah.
But that assumes that there is no boundary loss.
Or then, yeah, the pickup is pickup. Or you know that it is pickup. I guess your company is because of law, your pickup is not connected. Yeah.
Because we normally have resistive heaters, right? We typically have resistive heaters, so they're not necessarily uniform. That's why they use, like, yeah. So, but the industry standard is just find out the Q and find locally calculate the transfer coefficient.
Yeah, that's the best thing you can do.
Yeah.
Maybe, include something that involve, for example, there's no temperature, you can measure what is the temperature, that will give you some better idea how much you can go in. So that way, you can do this for different, the feeding to the model, you can cover it. What is actually community working time. So later you can go back from the temperature to the image, so that you are better.
So one question is, again, I completely did not understand when you said that using latent LED, we can actually transfer a lot more thermal energy and clarify.
When we use more, we have the temperature to gravity.
We have raise up the temperature of the system and still you can have.
Yeah, but if you do that for the increase the water temperature by 600 degrees, you can dissipate the thing. I think that's another. Yeah. Oh, okay, that's a very good one. So for now, we only test the water because water has very good simple part. But for the real application, most likely you are going to use refrigerator. But there's a drawback for electricity to be effective. The fluid must be colder. So the fluid for I guess for most refrigerators, they are not polar. So the idea will not work with refrigerators.
One of the studies you showed compares between experiments and simulations for AC and DC.
Yeah.
So I was just curious, what kind of simulation, what equations are being solved? And, are they just like?
But what is the mathematical model? Maybe a stroke.
Yeah, no, only as a first we need to I think the wavelength, because to track the interface. And also with the interface, we introduce some term for certain.
So you can measure it in experiments. You can measure it in experiments. That was meant to look at simulations for experiments, like we're comparing them.
Yeah, because we want to be the we want what are we to want to do now the interface of the that can also be done in experiment.
So you use the simulation to explore further.
Right.
Another question.
Yep.
This next speaker.
Okay, thank you guys.
So when you're back training, you talk about what I'm doing collaborating with NCS to do the use of model. So it's basically active in contact active. So we have a specimen, we have a vascular, send the liquid into that, or we regulate the temperature. So essentially some of the